You know, usually when we talk about the universe, we're talking about how vast it is.
Right, the sheer scale of it.
Yeah, how old it is, how far it goes on. But there's a different way to look at it that's actually, uh, I think, much more unsettling.
It's not about size at all.
No, it's about precision. Imagine you walked into a room and you saw a pencil standing perfectly balanced on its sharpened tip,
Okay.
but not on a table, balanced on the edge of a razor blade.
That is a very precarious image.
Right, and your instinct wouldn't be, oh, a strong breeze must have blown it there.
No, you'd assume someone placed it there carefully.
With terrifying exactitude, yeah. Well, today we are doing a deep dive into the idea that our universe, the laws, the math, the very fabric of reality looks exactly like that pencil. We're talking about the fine-tuning of the universe.
Which is one of the most hotly debated topics in modern cosmology.
Yeah.
And in philosophy, too.
Absolutely. And to guide us, we aren't just reading internet forums. We have a solid source today, a chapter by Robin Collins titled The Teleological Argument.
From the Blackwell Companion to Natural Theology.
Yes, and Collins is a heavyweight here. He's got degrees in physics and philosophy, so he's not just waving his hands around.
He's looking at the hard data, the initial conditions of the Big Bang.
Right, and his mission in this chapter is to argue that this highly specific structure strongly supports the existence of God.
Or theism, broadly speaking.
Yeah, theism over the idea that the universe is just a naturalistic brute fact. And as always, we're just here to impartially unpack the source material for you. We aren't taking sides, we're just laying out Collins's rigorous argument.
Exactly. And we really need to make a careful distinction before we go any further. When physicists use the term fine-tuning, they are not inherently saying designed.
Yes, let's clear that up immediately because people get tripped up on the word tuning.
Right. Fine-tuning is actually a neutral technical term. It just refers to the factual observation that the fundamental laws and constants of physics have to fall within an exceedingly narrow range.
A microscopic range, really.
Yes, for what Collins calls embodied moral agents to exist.
Embodied moral agents, which is his way of getting away from just saying life as we know it, right?
Precisely. He's not talking about simple bacteria on a rock. He means complex conscious beings who can think, make choices, actually do science.
You need a lot of physical complexity for that.
You need chemistry, you need stable environments, you need a massive amounts of time.
And Collins breaks down the evidence for this fine-tuning into three specific categories: the laws of nature, the constants of physics, and the initial conditions.
Let's start with the laws. This seems like the bedrock.
Yeah, before you can even roll the dice, you have to have the rules of the game.
That is the perfect way to phrase it. Collins points out that we just sort of assume the laws of physics are what they are, but they don't have to be.
Right, they could be entirely different.
And for life to exist, you need a very specific set of laws. You need gravity to pull matter together into stars.
You need electromagnetism to hold atoms together so you don't just have loose particles floating around.
And you need the strong nuclear force.
That's the one that binds protons and neutrons together in the nucleus, right?
Yes. Without it, the protons would just repel each other because of their positive charge. The atom would instantly fly apart.
So no chemistry.
No chemistry at all. And the balance here is critical. If the strong nuclear force were just slightly weaker, you wouldn't get any atoms other than hydrogen.
So no carbon, no oxygen, no us.
Right. And if it were slightly stronger, the universe would have burned through its nuclear fuel almost instantly.
There's another law he mentions that I think people often overlook, but it's crucial for us even sitting here right now: the Pauli exclusion principle.
Oh, absolutely. This is quantum mechanics. In simple terms, this principle forbids two electrons from occupying the exact same state at the same time.
So it forces electrons to sort of stack up in shells around the nucleus?
Exactly, which
Yeah.
is what gives matter volume. It's what makes things solid.
It's what stops me from falling through this chair.
Yeah, it's what makes complex chemistry possible. Without the Pauli exclusion principle, all electrons would just crash down into the lowest orbit.
Just collapse entirely.
Matter would collapse into a super dense inert soup. You wouldn't have chemical bonds. You basically need this specific rule to prevent the universe from being a homogeneous blob.
Okay, so step one, we have the right recipe book. But here's where it gets technically fascinating. Because it's not just the laws, it's the numbers plugged into those laws.
The constants.
Right, the constants. This is where we start talking about the dials of the universe.
Constants are the fixed numbers in the equations, like G, the gravitational constant.
Which determines exactly how hard gravity pulls. And Collins argues this dial is set to a razor-thin sweet spot.
He does. Consider the range of force strengths in nature. Gravity is incredibly weak compared to the strong nuclear force. It's about 10 to the 40th power times weaker.
That's a 1 with 40 zeros.
Right, a massive difference. Now, if you increase gravity by just one part in 10 to the 40th,
So you nudge the dial just a microscopic amount.
a completely microscopic amount. If you did that, stars like our sun wouldn't exist. They would burn out in a few million years rather than billions.
And life requires billions of years of stability to evolve.
Exactly, or the gravitational crush would be so immense that any organism larger than a pea would be completely crushed by its own weight.
Collins quotes the astrophysicist Martin Rees here, doesn't he? Saying that in a high-gravity world, insects would need legs like tree trunks just to stand up.
He does, yeah. But gravity is actually the easy one. The real headline grabber, the one that keeps physicists awake at night, is the cosmological constant.
The energy density of empty space? The vacuum energy?
This is widely considered the worst theoretical prediction in the history of physics.
That's quite a title.
It is, because based on quantum field theory, the energy of empty space should be huge, absolutely massive. But when we look at the expansion of the universe, the actual measured value is tiny.
And the difference between what the theory says it should be and what it actually is, it's staggering.
The discrepancy is roughly 10 to the power of 120.
That number is just nonsense. It's too big to even visualize.
To give you a sense of scale, there are only about 10 to the power of 80 atoms in the entire observable universe.
Wow.
So the precision required to cancel out the theoretical value and leave us with this tiny life-permitting sliver.
Right.
It's greater than the precision of picking one specific blindfolded atom out of the entire universe.
And why does this specific value matter so much? Why couldn't it just be bigger?
Because the cosmological constant acts as a sort of anti-gravity. It pushes the universe apart. If it were slightly larger, even by a tiny fraction, the universe would have expanded so fast that galaxies could never have formed.
Matter would just be dispersed into a thin, cold mist.
No stars, no planets, nothing.
And what if it were smaller?
The universe would have recollapsed in on itself almost immediately after the Big Bang.
So we really are balanced on a knife edge between blowing apart and crunching down.
Precisely.
Okay, so we have laws, we have constants. The third category Collins brings up is initial conditions. This is sort of the how is the table set question.
Right, this refers to the arrangement of mass and energy at the very beginning, the Big Bang. Specifically, the entropy or the level of disorder.
Right.
For a universe to have a history, to have galaxies and stars, and eventually us, it had to start in a state of exceptionally low entropy, highly, highly ordered.
And he cites Roger Penrose, the Nobel Prize-winning physicist, on the odds of this happening just by chance.
Penrose calculated the volume of phase space, which is basically all the mathematically possible arrangements of the universe. He concluded that for the Creator to pinpoint a universe with our level of order, they'd have to hit a target of 1 part in 10 to the power of 10 to the power of 123.
A double exponent.
It's a number so large that if you wrote a 0 in every single proton in the universe, you still couldn't write the number down.
That's unbelievable.
Collins uses a great analogy. He says it's like hitting a target the size of a single proton if the entire visible universe were the dartboard.
Okay, so the math is there, the tuning is undeniable. But here is where I have to play devil's advocate for a minute, because this is usually where skeptics get off the bus. They say, sure, it's unlikely, but unlikely things happen every single day.
The lottery argument.
Exactly. If I shuffle a deck of cards, the specific order I get is statistically near impossible, 1 in 10 to the power of 60 or something. But I still got that exact order. I don't assume a wizard rigged the deck, it's just the hand I was dealt. Why isn't the universe just a lucky hand?
This is the most common objection, and Collins addresses it with what he calls the likelihood principle. He argues that we have to distinguish between something being merely improbable and something being actually surprising.
Okay, break that down. What is the difference?
Go back to your deck of cards. If you shuffle and get a random jumble of suits and numbers, it's improbable, yes, but it's not surprising because you had no reason to expect any other result.
Right.
But imagine you shuffled and the cards came out in perfect numerical order. Ace, king of spades, then hearts, then diamonds, then clubs.
Okay, yeah, I wouldn't say, wow, what a statistical coincidence. I'd say you cheated.
Exactly. You would immediately infer a non-random cause. Why? Because that specific orderly result is epistemically probable under the hypothesis of cheating, but epistemically improbable under the hypothesis of pure randomness.
So it's fundamentally about expectation.
Yes. The likelihood principle states that evidence supports hypothesis 1 over hypothesis 2, if that evidence is more to be expected under hypothesis 1.
Okay, let's apply that to the universe.
Right, so in our case, a life-permitting universe is the evidence. Hypothesis 1 is theism. If a God exists who wants to create conscious embodied agents, a life-permitted universe is exactly what we would expect.
Makes sense.
Hypothesis 2 is the naturalistic single universe hypothesis. If the universe is just a brute fact, there's absolutely no reason to expect the constants to fall into their tiny, tiny life-permitting sliver.
Collins uses a thought experiment about an alien observer to explain this, right?
He does. Imagine an unembodied alien who knows all the laws of physics and math, but hasn't actually measured the constants yet. He looks at the math and sees that almost every single possible value for gravity or the cosmological constant results in a dead, lifeless void.
So the alien naturally predicts the universe is probably dead.
Right. If he then somehow discovers the universe is alive, teeming with galaxies, he should be completely shocked. Unless he adopts the hypothesis that someone intended it to be alive, then the surprise vanishes completely.
Now, there's a nuance here that Collins includes, which I think is really important, because it answers the skeptics who say, well, maybe life could exist with totally different constants. Maybe we just lack imagination.
Ah, yes. This is the concept of the epistemically illuminated region.
The what?
The epistemically illuminated region. Collins admits we can't know for sure what happens if you change the constants to wildly different numbers. Say you make gravity 1 billion times stronger. Maybe some weird, non-chemical plasma life could exist. We honestly don't know.
So how can we make a probability judgment if we don't know the whole picture?
Collins argues we have to look at the region we do know. The illuminated region where our physics still works and we can do the math. Within this range, we can rigorously prove that life is impossible almost everywhere except our tiny sweet spot.
Right.
He then applies the principle of indifference. Since we have no empirical reason to think the dark, unknown regions are teeming with life, and we know the illuminated region is almost entirely dead, the rational bet is that life-permitting universes are incredibly, incredibly rare.
So we shouldn't bank on a hypothetical magic physics we don't understand just to save the naturalistic worldview.
Exactly. We have to judge based on the data we actually have.
Okay, so the design argument is looking very robust. But science doesn't just roll over. Collins goes through the big objections, and we need to give them a fair shake. The first major one comes from physicist Victor Stenger. He created a simulation called Monkey God.
He did, yes. Stenger claimed that fine-tuning is basically a myth. He wrote a computer program that randomized the constants of physics and found that in many of these random universes, you still get long-lived stars.
And his argument was basically, if you have stars, you have energy. If you have energy, you could have life.
Right.
That sounds pretty damning on the surface. I mean, if a simple computer program can make life-sustaining universes, why do we need a designer?
Well, Collins dissects this quite ruthlessly. He points out that Stenger's simulation was frankly too simple. It was a classic case of garbage in, garbage out.
Oh, so?
Stenger used extremely simplified equations that completely ignored the critical complexities of stellar physics.
Like what kind of complexities?
Things like quantum degeneracy pressure and precise nuclear resonance levels. Stenger's simulated stars were basically just long-burning clumps of gas. But, as we discussed with the strong nuclear force, you don't just need a heat source. You need complex chemistry.
Right, you need carbon.
Exactly.
Yeah.
Collins argues that Stenger ignores the fact that even if you somehow get a star, if you tweak the nuclear forces even a tiny bit, you can't get carbon. You can't get oxygen. You might have a universe full of glowing light bulbs, but there's no chemical complexity to actually build an observer.
So Stenger proves you can mathematically make a shiny object, but not a habitat.
Precisely.
All right, let's move to the heavyweight champion of objections. The multiverse. This is the go-to explanation in pop culture now. Movies, TV shows, everything is a multiverse.
It is the most robust, scientific alternative to design right now. The logic goes like this. If there are infinite universes, and they all have randomly different constants, then statistically one of them has to be right for life.
We just happen to be in the winning lottery ticket because we obviously couldn't exist in the losing ones.
Right, this is called the observer selection effect.
It makes intuitive sense. If I roll 1 billion dice, I'm eventually going to get a run of 6s.
It does make sense. But Collins argues that the multiverse doesn't actually solve the problem, it just kicks the can down the road. He used a great analogy for this, the bread machine.
I love this one. Even a bread machine needs to be built.
Exactly. You can't just say multiverse like it's a magic word that solves everything. You need a physical mechanism to actually generate these infinite universes. In physics, the leading candidates are mechanisms like chaotic inflation or superstring theory.
Right.
But here's the catch. The multiverse generator itself must be highly fine-tuned to work.
So the machine that pumps out the random universes needs to be precisely designed.
Yes. For example, the generator needs to strictly follow the laws of general relativity and quantum mechanics. It needs very specific background fields to drive the inflation process. Collins argues that if you vary the parameters of the multiverse generator, it might just churn out infinite dead universes, or it might just collapse into nothing entirely.
So you haven't actually explained away the fine-tuning. You've just moved it from our universe up one level to the universe factory.
Exactly, you've just shifted the problem.
And that leads us to the weirdest and frankly most disturbing objection to the multiverse. The Boltzmann-Brain problem.
This is where the physics really gets closer to a horror story.
It really does.
Okay.
So, explain this for us. Why does the multiverse theory imply we should all be disembodied brains?
It comes down to thermodynamics, entropy, and statistical fluctuation. In a lot of these multiverse models, universes are born out of random fluctuations in a quantum vacuum. Now, statistically speaking, small fluctuations are vastly more common than huge ones.
Okay, that makes sense. It's much easier to get a tiny ripple in a pond than a massive tsunami.
Right. Now, think about what we are. We are observers living in a massive, highly orderly universe with billions of galaxies. That is a monumental fluctuation. Extremely low entropy. Extremely rare.
Okay.
But what is the bare minimum required to have a conscious observation? You don't need a whole universe. You technically just need a brain or a highly ordered processing center that thinks it's observing something.
A localized patch of order.
Exactly. A Boltzmann brain. Statistically, in an infinite random multiverse, it is exponentially more likely for a single brain to spontaneously fluctuate out of the quantum chaos, complete with completely false memories of a past, than for an entire orderly universe to evolve over billions of years.
So if the multiverse theory specifically, the chaotic inflation model, is true,
Then the vast majority of conscious observers in existence should be Boltzmann brains floating in the void, just hallucinating their reality.
but I'm not. I mean, I look around, I see a coherent, persistent physical universe. I'm clearly not a lone brain in the chaos.
And the fact that you are not a Boltzmann brain is incredibly strong empirical evidence against those multiverse models. The theory predicts you should be a freak, isolated observer. You aren't. Therefore, the underlying mechanism is likely false.
That is wild. It's like the multiverse proves too much. It explains how life could exist, but it predicts the completely wrong kind of life.
It predicts a deceptive, isolated existence. Since our everyday experience contradicts that, we have to deeply question the mechanism generating the multiverse.
Okay, so we've knocked down the monkey god simulation. The multiverse seems to have its own fine-tuning problems and this crazy Boltzmann brain issue. So we circle back to design. But then comes the classic retort. If God designed the universe, who designed God?
The infinite regression objection. Who designed the designer? Collins addresses this head-on.
And it's a fair question, right? If complexity requires a cause and God is infinitely complex, doesn't he need a cause?
Collins makes two distinct points here.
Rapid.
First, practically speaking in science, we don't need to explain the explanation to accept it as valid.
What do you mean?
Imagine human archaeologists land on Mars, and they find a spaceship. It's highly complex. It's clearly functionally designed. They would be fully justified in saying an intelligence built this. They don't need to know who the aliens were or who built the aliens to know the spaceship isn't just a weird rock formation.
That's a really good point. Identifying design is a separate scientific question from identifying the biography of the designer.
Exactly. But secondly, Collins points out a philosophical flaw in the objection. He argues that God isn't actually complex in the way a physical universe is. In classical theology, God is a spirit. He has no physical parts. He isn't composed of atoms or gears or forces. He is a simple, uncomposed entity, a mind.
So the logic that complex physical things need their parts assembled doesn't logically apply to him.
Right, the category just doesn't fit.
So where does this leave us at the end of the day? We've looked at the laws, the constants, the initial conditions. We've seen the major failures of the random naturalistic explanations.
We are fundamentally left with a universe that looks for all the world like a deliberate setup. The naturalistic explanation requires us to believe in a statistical coincidence of astronomical proportions. It's literally like winning the cosmic lottery 100 times in a row.
And the theistic explanation, as Collins lays it out, suggests that this incredible precision isn't an accident at all, it's a feature.
It strongly suggests that there is a mind behind the math, that the universe isn't just a cold, brute fact, but a deliberate habitat intended for observers like us.
I want to leave everyone listening with one final provocative thought from this deep dive. Collins has this great image near the end of the chapter of The Golden Planet.
Yes, this is a beautiful way to sum up the stakes of the argument.
He says, imagine an angel told a billionaire that somewhere in an infinite universe there is a planet made entirely of solid gold. Now, the billionaire could say, well, in an infinite universe, statistically, a golden planet has to exist somewhere. It's just a random thermodynamic accident. I'm not going to bother looking for it.
But no one would actually do that.
No, of course not. He'd hop in his spaceship and go find it immediately. The, oh, it's just a statistical accident excuse doesn't actually stop us from acting on valuable information.
And that is Collins's ultimate point. The fine-tuning of the universe is a massive clue. It's a map. We shouldn't just shrug our shoulders and say, well, mathematically, anything is possible somewhere. The clues are heaped upon clues.
The universe is clearly pointing somewhere. The real question for you is, are you willing to follow where it leads?
That really is the question.
Thanks for taking this deep dive with us today. Keep looking up.